Hey everyone, welcome back. Ready for another deep dive? Today, we're taking a look at something pretty incredible, supernovae. But not just supernovae in general. We're going to zero in on shock breakout, that very first flash of light that basically tells the universe, hey, a star just exploded.
It really is fascinating how it acts like a cosmic telegram. Like it gets sent out before any other signal.
Right, it's like a sneak peek behind the scenes. We've got some awesome source material to dig into today. It's a recent paper from the Astrophysical Journal. And get this, it goes deep on these brand new simulations of shock breakout. And they're the first ever 2D multi-wavelength simulations.
Really complex stuff. I mean, these simulations took 2 years to run on a supercomputer.
2 years, wow. I mean, you really start to grasp the dedication these scientists have when you hear that. Okay, so before we get totally lost in the details of these simulations, let's just take a step back for a second and remind ourselves what a supernova actually is.
Sure. So picture this. You've got a star way bigger than our sun, maybe 10, 20, even 30 times heavier. And these stars, they live life in the fast lane. They burn through their fuel much quicker than smaller stars.
Oh, I see. So they're like the rock stars of the universe.
Yeah.
Burn bright, fade fast.
Exactly. And when they run out of fuel, well, their core collapses in on itself, because of gravity. That collapse creates something super dense. Could be a neutron star. And that triggers a shockwave. It blasts the star's outer layers out into space.
And this shockwave, I'm guessing it's moving pretty darn fast.
Oh, yeah. Definitely supersonic speeds. And when that shockwave hits the surface of the star, boom, that's when you get that crazy bright flash, a shock breakout.
This is where it gets really mind-boggling. Because this flash, it's ridiculously short, right? We're talking just hours. And most of what we see is in X-rays and ultraviolet light, which we can't even see with our eyes.
That's right. Super fast, super bright, and mostly invisible, a fleeting little whisper from a dying star. But we can detect it with the right tools.
I know. It's like, why bother with something that disappears so quickly? What makes studying shock breakout so important?
Well, think about it. It's all about timing. That shock breakout is like our very first heads up that a supernova is happening. It's like long before the main light show even starts, we get this little cosmic telegram announcing, hey, things are about to get wild over here.
I get it. So it's not just about knowing that a star went supernova. It's about that early signal, right? It gives us a look into the final moments of the star, and maybe even a glimpse into the environment around it.
You got it. So the star, it's been living its whole life inside this bubble. Astronomers call it the circumstellar medium. It's made up of all the stuff the star has shed over time.
Gas, dust, all that good stuff.
Exactly. It's like the star's own little cosmic fingerprint. And when the shock breakout happens, it slams into this material, leaves clues behind about the star's history.
Wow, that's amazing. Like, we're getting to peek at the star's diary right before it goes out with a bang. But how do we even study something that disappears so fast?
That's where these mind-blowing simulations come in. Scientists are modeling the physics of shock breakout in such detail, and they can compare what their models predict to what we actually see when we observe supernovae.
It's like having a Rosetta Stone for these fleeting cosmic events.
Exactly. It helps us decode what's going on.
So this 2-year supercomputer simulation you mentioned, they didn't just pick any random supernova to model, right? They focused on recreating supernova 1987A.
Yep, 1987A, and there's a reason they picked that one. Relatively speaking, it was close to us, and astronomers were able to gather a ton of data on it, so it makes a perfect test case for these detailed simulations.
So it's like having a front row seat to one of the universe's most spectacular events. What did those simulations show? Anything surprising?
Well, let's just say these simulations, they revealed some pretty wild stuff, things we didn't really expect.
Oh, come on. Don't leave me hanging. Tell me all about it.
Okay, so first of all, they found that the stuff around the star, that personal bubble we talked about, it has a much bigger impact on the shock breakout than we thought.
So it's not just about the star itself. It's about the environment around it, too.
Right. It's like the environment acts as a prism, It splits the light from the shockwave in all sorts of weird ways.
Whoa, okay. I'm trying to picture that. So what does that mean for us, trying to understand these events?
It means we can actually use the light from that shock breakout to learn about the star's history, like what it interacted with before it went supernova.
That's so cool. It really is like reading the star's diary, huh?
Exactly. Oh, and here's the other big thing they found. Fluid instabilities. Basically, during the shock breakout, things get, kind of chaotic.
Okay, instabilities, that sounds a little ominous. What exactly are we talking about here?
Think of it like shaking up a bottle of champagne. Right before you pop the cork, all those bubbles forming. It's kind of like that.
Okay, I'm picturing it. champagne supernova.
Yeah, something like that. But these instabilities, they make the shock breakout flash even brighter and longer than we expected.
So it's like they're adding fuel to the fire, making the whole thing even more dramatic.
Yeah, you could say that. And this is why those 2D simulations are such a big deal. They're giving us a much more realistic view of what happens.
It sounds like these simulations are changing everything.
Yeah.
But hold on a second. Let's bring this back down to Earth for a minute. We've got all these incredible new telescopes coming online, like the James Webb Space Telescope. How do these simulations help us with all that?
Oh, they're going to be crucial. Think of the simulations like a roadmap, a guide for figuring out all the data we get from those telescopes.
So it's like we're finally getting the tools we need to understand these incredible events.
Exactly. And with James Webb being able to see in infrared, that's going to be huge. We'll be able to see through all the dust and gas that usually hides these events.
That's so exciting. Better observations and these simulations to help us understand it all. Sounds like a golden age for supernova research.
It really is. Think about all the questions we might be able to answer. How supernovae evolve right from the very beginning. Maybe even crack the code on how elements heavier than iron are made.
Wait a minute, you're talking about the stuff that makes up planets, like Earth.
That's right. Supernovae are like giant cosmic factories. They forge those elements and spread them throughout the universe. By studying shock breakout, we're basically tracing the origins of, well, everything around us.
Wow, that really puts things into perspective. It's incredible how these tiny flashes of light can tell us so much. But there's this one question that I think everyone's wondering right now.
Let me guess. You're wondering if we can predict when a supernova is going to happen.
Bingo. I mean, with shock breakout being that first signal, it makes you think, what if we could actually see these things coming in our own galaxy?
Huh. Imagine the headlines. Supernova tonight. Don't forget your sunglasses.
Right. But seriously, with these new simulations and our amazing telescopes, could that be possible one day?
Well, astronomers have been trying to predict supernovae for a long time, and it's still a really tough challenge. But these simulations, they're definitely a step in the right direction. The more we learn about shock breakout, the closer we get to maybe, just maybe, being able to say, hey, that star over there, yeah, it's about to go supernova.
Yeah, that would be absolutely incredible. It would be like having a front row seat to the most spectacular show in the universe right here in our own cosmic backyard.
It really would. Imagine the data we could get. It could completely revolutionize our understanding of supernovae.
So even though we can't predict supernovae with, 100% certainty just yet, it seems like these simulations are bringing us closer.
Definitely. And even if prediction stays out of reach for now, these simulations have already opened up so many new doors for us.
It's amazing to think that these events, they happen so fast, but they hold so many secrets. It makes you wonder what else is out there waiting to be discovered. But for now, I think we've done a pretty good job of exploring the amazing world of supernova shock breakouts. This has to be one of my favorite deep dives.
It's been a blast exploring this with you. I hope our listener is feeling just as inspired by all this as we are.
So to our listener, keep looking up. Every star up there has a story to tell. And who knows, maybe one day we'll be able to tell you exactly when one of those stories is about to reach its explosive climax.
Until then, keep exploring, keep asking questions, and keep diving deep into the cosmos.
And that's it for this deep dive. See you next time for another adventure into the unknown. I mean, it wouldn't be much warning, would it? Given how fast these shock breakouts happen. But still, could we? Could we create some kind of early warning system?
That's a great question. And it really gets to the heart of why we study shock breakout in the first place. Right now, it's kind of like we're trying to understand fireworks, but we only get to see the big final burst. We miss the whole buildup, the way they're designed to explode. Shock breakout gives us a chance to see that with supernovae.
Oh, I see what you mean. Like, instead of just the grand finale, we get to see a little bit of the behind-the-scenes action, right?
Exactly. And those simulations we were talking about, they're basically giving us a cheat sheet, like what to look for in the light that tells us, okay, this star is about to go boom.
It's like a decoder ring for the universe's most epic fireworks show.
I like that. And think about it. As our telescopes get even better and our simulations become even more detailed, who knows what we'll find? Maybe we'll discover entirely new types of supernovae, or even figure out some unexpected connections between these events and how galaxies evolve.
Feels like we're just scratching the surface of something huge here. And all thanks to these fleeting little flashes of light.
It's true. Even in these events that last for just a few hours, there's so much we can learn. About where elements come from, how stars live and die, maybe even about the fate of the universe itself.
Well, I'd say we did it. We explored the wild world of supernova shock breakouts. This one was definitely a highlight for me.
It's been awesome diving into this with you. I hope our listeners feeling as blown away by all this as we are.
So to our listener, don't forget to look up at the stars every now and then. Each one has a story. And maybe, just maybe someday, we'll be able to tell you when one of those stories is about to end with a bang.
In the meantime, keep exploring, keep wondering, and keep diving deep into the mysteries of the cosmos.
And that's a wrap for today's deep dive. We'll catch you next time for another adventure into the unknown.